I've got up here on the board the greatest integer function. The notation for that is these double brackets around x. And what that means is that the y value is just the greatest integer that's less than or equal to x. Now let's remind ourselves of what the integers are. The integers are going to be an infinite set. I'm actually going to start in the middle of it. 0 is an integer, and the counting numbers, 1, 2, 3, and that goes on forever and ever and ever. Okay, so we're not including fractions, although integers can be written as fractions. 2 is the same as 2 over 1, but if I reduce it, it doesn't look like a fraction. And if I write it as a decimal, all of the digits to the right of the decimal would be 0. Okay, so that's what we call the whole numbers right there, is 0 and the counting numbers, but the integers include the negatives. So it would include -1, -2, -3, and that goes on forever and ever and ever in the other direction. Okay. So let's just try evaluating the greatest integer function at a few points. And as we do that, we're going to ultimately try to sketch the graph of this. So I'm just going to mark off on the x-axis my integers, because it seems like those are going to be fairly important in defining this greatest integer function. Okay, oops, this should be the greatest integer of x. Okay. Let's try first of all evaluating it at an integer. Let's just say I wanted to evaluate it at 2. Okay. Well, here on the x-axis there's 2. Okay. I'm looking for the greatest integer that's less than or equal to 2. Well, all of the integers that I've marked off here that are to the left of 2 are less than 2. But you'll notice this is an inclusive inequality. 2 is equal to 2, so that makes it less than or equal to 2. So all of the integers that are less than or equal to 2 would be everything 2, 1, 0, -1, etc., etc. And if I want the greatest one, I want the one that's furthest to the right on the number line. So the greatest integer function evaluated at 2 is just 2. So if I'm graphing this, there would be a point 2, 2 on the graph of this function. Let's evaluate at another integer. Let's try a -1. Let's try -2. So here's -2 on the x-axis. Now, all of the integers that are less than or equal to -2 would be everything that's to the left of -2, or because -2 is an integer at -2. So it's -2, -3, -4. If I want the greatest one of those, I want the one that's furthest to the right. It's going to be -2. So I'm going to have a point here at -2, -2. And in fact, it will always be the case, if I plug in an integer, that integer will be the greatest integer that's less than or equal to itself, because it's always equal to itself, and everything else that meets this condition is going to be smaller than it. So I'll have points at -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, etc., etc. Now let's see what happens if I plug in a number that isn't an integer. So let's say I wanted to plug in 1.5. Well, on the x-axis, 1.5 is here, in between 1 and 2. All of the integers that are less than or equal to it would be to the left of 1.5. So I'm going to just slide to the left until I hit an integer. The first one I hit is 1. So that is going to be my y value. That's the biggest integer that's less than or equal to 1.5. If I were to plug in 1.6, it would be the same thing. Just looking on the x-axis, here's 1.6. The integers that are less than or equal to it are all less than that, because 1.6 isn't an integer. But the biggest integer that's smaller than it is 1. So I'm sort of using the x-axis just as a number line to figure out what's the thing that's furthest to the right, but that's to the left of that number if the number isn't an integer. Okay. And then that just tells me what the y value is. So at 1.6, we're also at 1. And in fact, if I plug in any number between 1 and 2, the biggest integer that's less than or equal to that is going to be 1. So we're just going to have a horizontal line here until we hit 2. As soon as we hit 2, we're going to jump up to a y value of 2. But if I plug in any number strictly between 2 and 3, so any number in this interval, 2's going to be the biggest integer that's smaller than numbers in that interval. So we'll be at a height of 2 until we hit 3, at which point we'll jump up to a point 3, 3. And that pattern continues. So from 0 to 1, we're at 0. Once we hit 1, we jump up to a y value of 1. So I'm getting a bunch of these intervals where I'm including the left endpoint, but not including the right endpoint. And those intervals are just giving me horizontal line segments in between consecutive pairs of integers. And this pattern just continues forever. So that's an example of something that's a piecewise function, but where there are infinitely many pieces that I have. And so we've developed this notation to describe the rule for determining what those pieces are. This actually shows us a pattern that often shows up in piecewise functions that might occur in the real world, where up until a certain point you're at a value and then there's a jump up. Great example of that would be parking rates. So let's suppose there's a parking lot where you've got to pay to park, and the rule is that if you park for less than 1 hour, it's free, but after that, it's $5 for every hour or portion of an hour after that. So, let's see. If I'm putting time here, I'll put hours on this axis and the cost to park on the vertical axis. Okay. Now, there's no such thing as negative time, and I'm not going to be paying a negative amount of money. So this is something where I really only need the first quadrant in my graph. Okay. But if here's 1 hour, and 2 hours, and 3 hours, and 4 hours, and on the vertical axis, I'm just going to mark things off in multiples of 5. 5, 10, 15, etc., etc. Okay. All right. So, it's free if I park for less than an hour. So, until I've parked for 1 hour, I'm going to be paying $0 to park. But as soon as I've parked for 1 hour, it's going to cost me $5. Okay. Now, if I park for an hour and a half, that's going to cost me $10, because it's $5 for every hour or portion of an hour after that. So as soon as I go more than 1 hour, that's the first hour that cost me the $5, plus I'm paying $5 for the portion of the second hour. So we would jump up to 10. Now if I park for exactly 1 hour, it's going to be just the $5. But as soon as I go over that, I'm paying for that first hour and part of the second hour. And so that's going to take me until 2 hours. If I park for exactly 2 hours, I'm still paying that $10. But as soon as I go over 2 hours, I'm paying $5 for the additional time, part of that third hour. So we would jump up to 15 and stay at 15 until we hit 3 hours. And that pattern would continue. So once the pattern starts, this looks very similar to the greatest integer function, with the exception of the fact that now I'm including the right endpoint of my interval rather than the left endpoint. And also, I've got this one sort of oddball. They're nice to us if we park for less than an hour, so they're not charging us $5 for part of the first hour. They're only going to charge us $5 if we park for exactly 1 hour. And then as soon as we go over that, jumps up to $10. As soon as we go over 2 hours, it jumps up to 15, and that pattern continues. So these jumps are going to be things where you've got a pricing scheme that's based on certain units of time, where once this much time elapses, you jump up to the next amount that you've got to pay.